So now we're going to look at the part of the modeling process that involves choosing a loss function and using it to fit the model. And we'll look at two different types of loss functions that we'll frequently see in this course. So what do I mean by a loss function? This is a mathematical way of measuring how good or bad a prediction is. Ideally, I want the loss to be small if my predicted value is close to the actual value, and high if it's far. I actually have a lot of different ways I can define loss functions, and the choice depends on my estimation risk. Depends on the estimation task. There are actually a lot of definitions of loss functions. The choice of loss function will affect the accuracy as well as the computational cost. And what you choose is going to depend on what you're trying to estimate. If your outputs are quantitative, that will affect what types of loss functions you can choose versus if they're qualitative. Also, whether or not you care about outliers, or if you want all errors equally costly, this will influence which loss function you may choose. For our purposes, we're going to look right now at loss functions for quantitative data. And there's two different loss functions we'll introduce in this class. The first is called the squared loss, or you'll often hear it called the L2 loss. And notice what happens in this case if your prediction is close. So here's my prediction, and here's my data value. If the prediction is actually close to the data value, I am going to have low loss. And if my prediction is far from the data value, I will square that difference. So I'm going to penalize it a lot. Squaring is not the only option, though. The other version we're going to look at is when you take the absolute value. And this is often called the L1 loss. This L2 and L1 notation actually comes back to some math theory around what are called mathematical norms. And they're called L2 norms and L1 norms that are based on these quantities. And so for our purposes, we're not going to dive into that theory behind norms, but we will point out the names just because you may hear them referred to this way. So notice with using the L1 loss, yes, when you have your prediction far from the actual value, you do get high loss, but not as high as you do with this squared loss because you're just taking the absolute value, not the square. Now, so far I've defined the loss just in terms of the difference between a single data point and the prediction. But overall, for an entire model, I actually want to look at my average loss across all data points. That quantity, or that idea of average loss, is something we're also going to call empirical risk in this class. And notice that this is really going to be a function of your parameter theta. This is going to be based on the sample itself. So it's really telling you how well the model fits the particular sample data you have, not necessarily the entire population. But hopefully these are close, and we'll talk about some ways to use inference to determine how close they are. There are some shorthand terms that we use for the average loss, depending on which loss function we choose. If you use the L2 loss function, then the average loss is called the mean squared error, or you'll see the acronym MSE. If you use the L1 loss function, then the average loss is called the mean absolute error, or the MAE. So the next question is, given a loss function, how do you choose the best parameters of the model for your data? This is the idea of what we call fitting a model. So in this case, I'm going to go back here. We're going to assume for this first example that we're going to use the L2 loss for this first example. We're still sticking with our constant model. So let's rewrite this, or use the L2 loss to rewrite what our average loss function is going to look like. This is the average loss function in general for any model here, but now we're going to replace this with our constant model. And we're going to fit the model by finding the value of theta naught that minimizes this entire average loss. Okay, so the goal here to fit the model is find the value of this that gives me the overall minimum mean squared error. All right, when it comes to minimizing functions, we have calculus at our disposal, at least for a simple model like this. When we get to more complicated models in the future, we're going to need some numerical approaches to find the minimum. But fortunately, for something as simple as this, we'll be able to do it visually and using calculus. So one way you could do this is if you know the data, like we do in our specific example of the boba tea, you can modify this function by just plugging in the values first. And then I want to find the value of theta naught that minimizes this function. You may remember when you have a function like this where my highest power of the variable is just squared, this is called a quadratic, and so it's going to have the shape of a parabola. And so we just need to find the min, the location of the minimum of this parabola. Thinking of this as theta, and this is r of theta. The second approach is we could do this in general, which we're going to look at. And so I don't have to make it depend on specific data points. I can leave the data points in the equation and use calculus to help me find the general case. So we're going to do both. But let's start with the first case just to give you some intuition. So this is the loss just for my first observation. So I sold 20 cups of boba tea, and I'm going to now try to minimize this function. The minimum of this occurs where you would probably think, which is just that theta is equal to 20. This is a quadratic, so this is a parabola. The min occurs here. This function, though, is the one I actually am interested in because I want the average loss across all observations to be as small as possible. This is still a quadratic. I'm going to plot it here. And you're going to notice, by no coincidence, that the center of it here is 25, which may be one of the values you picked when I was asking you to guess what constant you would use as a prediction for the number of sales. But we're going to see mathematically exactly where this comes from. So how did I find the minimum other than just graphing? This is where I can use the idea of a slope. So if you remember a slope of a tangent line from calculus, I always like to have people picture that they're snowboarding along a curve and it's the rise over the run of their snowboard. And so the way calculus helps us find max or mins is we look for where the slope is 0. And that's a candidate for where I might have a max or a min. So we look here or here, places where I have a slope of 0. Then once you find those, you have to check and see whether it's a max or a min. But let's start with that first part here. So this is the generalized way of how we can find the minimum of this average loss function. Taking the derivative with respect to theta naught, I'm going to solve for where it's equal to 0. That's just going to give me possible places where I have a local max or min. And then on the next page, we're going to have to check if it's a min or a max. So this first step is just to find where my slope is 0. So it turns out that the derivative of a sum is the sum of derivatives. So now I'm just taking the derivative of this with respect to theta naught. I can use a chain rule, and then I can do some simplification, just pulling out the -2. And now I'm going to set this equal to 0. And notice the product of two things can be 0 when either of these pieces are 0. So either this is 0 or this is 0. And there's not a way for -2 over n to ever equal 0. And so I'm actually just going to look at where the second term, the sum, equals 0. I can separate out the sums and then simplify. And notice a repeated sum of a constant ends up just being n times that constant. So now I have this whole thing equal to 0. Let's move this to the other side. And then we will simplify by solving for theta naught. So I'm going to divide both sides by n. And that's going to lead me to theta naught is, Yes, that's correct. The mean of your y data points. And that's exactly what we found. That's why we ended up with 25 in the previous picture. Now, I will be careful here because these are candidate places for where I might have a max or a min. Right now, I found that a max or a min may occur at y bar, or my sample mean. Let's go ahead and show it's actually a min. To do that, we have to look at the second derivative, and we show that the second derivative is always positive, which means I have concave up behavior, which means this is in fact a min. So how do we interpret this? That means that the mean is my optimal parameter when I'm trying to fit the constant model using mean squared error. This holds true regardless of what data sample we have, and this should provide some intuition as to why the mean is such a common summary statistic that we use. Another interesting fact is to notice what is the mean squared error when I actually plug in the mean. What's the smallest I get this to be? And if you look here, this is directly the definition of the sample variance. So if I'm asking for the minimum of my mean squared error, min it can be over all possible inputs of theta naught ends up being equivalent to the sample variance. This notation here, argmin, is actually asking for what is the input value of theta naught that gives me the minimum of this. So argmin is actually the mean. This is the difference on the plot on the previous page between asking where this occurs, so 25 is the argmin, and then asking what is the actual mean squared error at that point, which ends up being the sample variance of your y values. So these are terms that you may see in future classes as well when you see argmin versus just min. And so I'd just like you to think the argmin is asking what's argument and minimizes this function. A lot of times we're mostly going to be interested in what the value of the actual theta is, because that's what we're going to use in our model. We will sometimes want to compare this minimum mean squared error across different versions of the model. So sometimes we'll be interested in that. So to recap, we decided we were going to use the constant model. We chose the L2 loss, which led us to minimize the mean squared error. And we found the constant that minimizes the mean squared error is actually the mean y bar of our data. So if we go back to the original question we started with, I'm at this local boba shop, I'm estimating the sales each day. I would use the mean of these 5 numbers as my model for how much I'm going to predict I'm going to sell the next day. Now, one question you may be noticing or asking is, well, this was really dependent on the loss function we chose. So how would our prediction change if we instead had used a different loss function? Let's look at now the same constant model, but now we're going to use the mean absolute error. In particular, that involves using the absolute loss at each data point. And so here is our new average loss that we're going to try to minimize. And I now want the value of theta naught that will make this the smallest. Let's look at it visually first. So let's look just at what happens with our absolute loss on our first observation. If I plot this function, this is an absolute value. So this is a piecewise linear function, looks like this v. And if I only have this function, then the min will occur when theta naught is 20. But this is not my only observation. I actually want to think of what is the average loss, and that's what I'd like to minimize. And it turns out if I go plot this is a piecewise linear function, and it's minimized at the value of 22. Okay, so for this data set, if I were going to use L1 loss and mean absolute error, I would actually predict 22 instead of 25. Let's generalize this. How did we get this value 22 from this original data set. You may be noticing it's the value that's directly in the middle, as in there are two values that are less than it and two values that are greater than it. And that's not a coincidence. It is, in fact, the median that will minimize the mean absolute error for the constant model. But let's prove that more generally using calculus. So just like we did before, we're going to take the derivative with respect to theta naught. Now I have to remember how to take the derivative of an absolute value. I'm going to give you some intuition visually, and then we'll look at it mathematically. This is I want the slope of my tangent line. So you can notice if I'm here to the left of this v, like the vertex, my slope will be -1, or it's going to depend on exactly how sharp of a curve that is. But if this is just y sub I minus theta naught, my slope will be -1. And to the right, my slope is +1. And actually at the vertex, the slope is not defined. What I just showed visually, we can show mathematically as follows. So here is the definition of absolute value in terms of a piecewise function. And then I can take the derivative of each of these with respect to theta naught. And that's going to give me -1, like we talked about, if you're to the left of the vertex, +1 if you're to the right. I am going to ignore the exact value at the vertex right now since the derivative is not defined there. There's a little bit of hand waving here, but it turns out it will not affect the results of our proof to ignore that point. So now I want to add up. I'm either going to add up a value of -1 if my data point is greater than theta naught, and I'm going to add up a value of +1 if my data point is less than theta naught. So that's what we have here. And this is basically, when I'm writing, is a sum. And this is just saying the number of data points, y sub I, that are greater than theta naught. I'll be adding a -1 for each one of those. The number of data points that are less than theta naught, the theta naught again is this constant I'm trying to find, I'll be adding a +1. Now, if you recall, when I'm trying to minimize a function using calculus, I'm now going to set this derivative equal to 0. And before we do that piece, I'm just adding a little caveat here that I am right now just looking at strictly greater than, strictly less than, because thankfully it won't change the result. That takes a little bit more math to dive into. All right, so we're going to take this now and set it equal to 0. And yes, this is just summarizing that what I'm summing up is a -1 if our observation is greater than our prediction, +1 if our observation is less than our prediction. Set it equal to 0, and now I can realize the coefficient out front's never going to be 0. So I'm basically setting this equal to 0. And that's going to be equivalent of actually moving this sum over to the other side. And so I'm looking for when these two sums are equal. Now this seems a little tricky. We haven't done something like this before. So where do we go from here? What does this really mean? All right. The constant model parameter that minimizes my mean absolute error must satisfy this. That's where we've gotten to so far. And what does this mean? This is the number of observations greater than the prediction and the number of observations less than the prediction. If I need those two to be equal, well, that means I need an equal number of points to the left and to the right. That's actually the definition of the median. So in our example, the point in green is our median. It's the value in the middle. And that's how we ended up with 22. So let me summarize. First, I'm either choosing an L1 or an L2 loss. And then I'm using that to come up with my average loss, and I'm minimizing that average loss. The objective function, again, was my average loss. I took the derivative with respect to 0. I set equal to 0. I solved. Now there's some hand waving, more hand waving, because technically I need to check that the value that I found is actually a min. Mean squared error is going to have a property that guarantees that this will be a global minimum, so we actually don't even have to worry about checking it. It's much harder to prove convexity for mean absolute error, but it is true for our case here that the value that we got, the median, is going to be the minimum of my loss, my average loss function. So what do we get this round? Same model from the beginning, a different loss function led us to a different solution for the model itself.